Yep.
Perfect. But here you cannot. Okay. So today's agenda, we are going to be talking about, we're finishing up synchronization. So we've got, and just a second, we're missing. Yeah, just. Hold up, y'all. There we go. One connection I'm missing. And did I have a question or not? No? Okay. So today, come on, something is, there we go. Okay, synchronization, going to finish it up. And specifically, we're going to be talking about deadlock. Then we're going to go over problem 1 on the homework assignment. And finally, we are going to start talking about sockets. There is no quiz today. Okay, so next quiz is not until Thursday, so no quiz today. And that is because I don't think we're going to get all the way through sockets today. So I postponed that off until Thursday. Okay, so last
Can I ask a clarifying question?
Yes, go ahead.
Do you mean there's no quiz due today, or there's no quiz over today's material, or?
There is no quiz that is going to be due on Thursday. So no quiz over today's material. So no quiz due Thursday. So basically, Thursday's quiz covers the material from today and Thursday. Okay. Other questions? Okay. So last time with synchronization, we covered 3 methods. You can do fork, you can do join, and you can use wait to enforce what would be called a happens before relationship. Now, unfortunately, the original version of Java's concurrency package was a bit heavy-handed with locks, or not maybe heavy-handed, but didn't give you a lot of control over locks. And so there are situations that can occur where you end up with deadlock. Okay, it's a situation where 2 threads hold resources that the other thread requires in order to continue. So normally, remember what is really happening here with resources is we are locking them. So let's say we have thread A and thread B. And thread A has already resource 1. And B has resource 2. Each of them has a lock. And now A needs to get access to resource 2 in order to continue. So A waits, goes into a waiting state. So A waits until B finishes. So B now resumes execution, but at some point it decides it needs resource 1 in order to continue. So it goes into a waiting state, waiting for A to complete. And this is deadlock, because now neither A nor B can make progress. And so they will just sit there infinitely or indefinitely until someone kills them, okay? And the more recent versions of Java give A and B ways to handle this situation by allowing them to back out of their requests for resources. They basically can say, I will wait for this resource for, say, 10 seconds. And if I don't get the resource, please awaken me and I will take some other action. Or it can say, if this lock is not available now, perhaps I won't try to get it. So there are ways that the existing versions, the more modern versions of Java have for dealing with deadlock. But the old version that used synchronized methods didn't allow you to A, check whether some other thread already owned the lock on an object, and B, once you called the synchronized method, it doesn't allow you to ever back out by saying, okay, if I'm stuck here for 10 seconds, then let me say shut down or something else. So basically, first of all, with synchronized methods, you can't know before you call the synchronized method whether you will get control of it or not. And 2, once you call it, you're stuck. You can't back out. Okay, so this led to deadlock situations. The tutorial has one example that I always have trouble with, so I came up with another one to illustrate deadlock. So my example, because I do like competition. So I created a class called contestant, and the class has a name of the contestant and their score. And the heart of it is that we want to compute a winner. So we are going to get the name of our opponent. And very simply, what we're going to do is compare our score with the opponent's score. So we're going to get the opponent's score. And all we're going to do is check the 2 scores. If our score is greater than the opponent's score, then you say, I defeated my opponent by a score of whatever to whatever. If the score is less than the opponent's score, I was defeated, and otherwise it was a tie. Okay, so it's a very simple comparison. All you're doing is comparing your score against the opponent's score. But to make things interesting, I synchronized all the methods. So compute winner is synchronized, get score is synchronized, get name is synchronized. The only thing not synchronized is the constructor. Okay? So then I create 2 contestants, Alphonse with a score of 50 and Gaston with a score of 45. And I create 2 threads. One where Alphonse is going to compute the winner of his matchup with Gaston, and a second thread where Gaston computes the winner of his matchup with Alphonse. Okay? So what we would expect, let's get rid of these synchronized methods to show you what would happen without them. In fact, just get rid of those. Okay, and we get Gaston. I have some print statements in there, but basically Alphonse calls get name, and gets Gaston's name, announces that Gaston is my opponent. And you can see here, Gaston now starts and announces that Alphonse is my opponent. And after some printing of stuff, Alphonse, let's see, Gaston announces that Alphonse defeated me by a score of 50-45, and Alphonse announces that I defeated Gaston by a score of 50-45. Now, the first thing, now let's go to synchronized methods. Yeah, you can't put the synchronized right there. And that's all I get. And I can wait here for the rest of the hour and I will get no further. It's a deadlock situation. So let's trace what has happened, okay, to see what is going on here. Okay, first I'm just going to quit. Okay, so we created Alphonse and it called compute winner. Okay, so the first thing that Alphonse tried to do was print out the name of his opponent. So he called get name with his opponent. And that was fine because at this point, Gaston wasn't yet running. So you can see get name printed out, Gaston printed out the fact that get name was called, printed his name and returned it. And at this point, Alphonse printed out this statement. Now, when you print something, you give up the CPU. That's an important thing to know. That's an interrupt. So, because this is important for the sockets too. So when you read or write, reads and writes cause interrupts. That force a thread to relinquish control of the CPU. Okay, so that's very important. So when I ran this program, I got to here. So Alphonse called get name to get Gaston's name, and he was able to print out Gaston as my opponent. At this point, Alphonse gave up the CPU. Okay, so at this point, Alphonse has given up the CPU. So Alphonse printed message. So Alphonse, Gaston. Okay, printed message. Okay, and then gives up the CPU. So now on the timeline, so this is time running this way. So now Gaston starts because it's Alphonse has given up the CPU. So it calls Gaston gets compute winner called. Okay, so first thing that Gaston tries to do is Gaston tries to call opponent.getName. Okay, But the problem is, right now, who has the lock for his opponent is Alphonse. And right now, Alphonse holds the lock on Alphonse's object because Alphonse is stuck right now in compute winner. Okay, so right now, Alphonse holds the lock, gives up the CPU, but holds lock on Alphonse because he's still in compute winner. Okay, so Gaston starts, gets lock for Gaston, calls Alphonse dot get name. Okay, but Alphonse holds the lock, so is forced to wait. Okay, because Alphonse holds the lock. While Alphonse holds the lock on Alphonse, no one else can call any of the synchronized methods. Okay, so with Gaston forced to wait, Alphonse comes back on the stage. So we reintroduce Alphonse, and Alphonse says, great, I'm ready to go again. Get rid of this, we don't need the flush. And Alphonse goes for Gaston's score right here. Well, that immediately, okay. So Alphonse tries to get Gaston scored. And is forced to wait because Gaston holds the lock on Gaston's object. At this point, we've deadlocked and no further progress will be made. There's no way to get out, okay? No way to set a timer that one of them times out after a certain time. There's no way for main to cause an interrupt that either of them can track. So you can try to, in main, you can try to call the interrupt procedure, but they're not going to hear it. As long as they're sitting, waiting on these synchronized calls, they can't check the interrupt flag until those calls have returned. You're just stuck, and there's no way out. So this was the problem with synchronized methods. And this gets fixed with the high-level Java concurrency locks that we'll talk about next Tuesday. But this was the problem you could run into in old style Java using the lower level concurrency mechanisms. Okay, so questions about any of this? Okay. So there's a couple less common situations. One is called starvation. So and that occurs when a thread cannot get access gain access to a resource so this is different than deadlock because it just may be this is, for example, a low priority thread. And therefore, higher priority threads always get the resource in preference to this thread. And therefore, it starves while other threads continue to make progress and succeed. This often happens with CPUs where you have priority and higher priority processes run in preference to lower priority processes. Now, the way that is typically handled by an operating system is a thread's priority is gradually increased. until its priority is so high that it gains the CPU. So that's a common strategy for, in effect, promoting low priority threads until they eventually have a high enough priority that they get access to the resource. But sometimes they could be equal priority, but for some reason, the scheduler keeps scheduling some other thread to get the resource. This is normally a problem for the OS rather than a problem in your own programs, but it can happen. It's just not something we normally worry about. And then there's another form of failing to make progress called liveness. And this is where processes are so busy. Let's see what the definition. Oracle gives a good definition, so I'm actually going to go for the Oracle definition of it. It's called LiveLock. I'm sorry, it's not liveness, it's LiveLock. So here it is. With LiveLock, the issue is that threads are not blocked. They're simply too busy responding to each other to resume work. Okay, the classic kind of example, two of us are walking down a hall and we see that we're going to collide, okay? So I move to the left. The problem is, as I move to the left, you simultaneously make a decision to move to the right to also avoid the collision. Unfortunately, because of our actions, we're still on a collision course. So now I duck back to the right, but you simultaneously duck to the left to also avoid the collision. We're still on a collision course. That's called LiveLock. Basically, we keep responding to each other, but our response perpetuates the problem and doesn't solve the problem. Okay, again, this doesn't happen so often. Deadlock is our biggest worry. Starvation is our second biggest worry. LiveLock doesn't really occur that frequently, but is something you should be aware of. So it's not liveness, it's LiveLock. Okay, so threads fail to make progress because they keep responding to each other. It's as though you keep doing administrative tasks rather than something that allows you to actually solve the problem. Okay, so those are the three things: deadlock, starvation, LiveLock, problems with synchronization. Okay, so I gave you the problem. I don't actually give you a solution until next week, but it's important to know that this is an issue with Java's synchronized methods. Okay. And I believe, I actually just thought occurred to me, I didn't check this before class. I suspect that if I made these synchronized, it's possible if I made them synchronized blocks, it might or might not work. I need to think about that one, but certainly it's an issue with synchronized methods. I don't know if I could have escaped this problem with synchronized statements or not. Not going to think about it just now. Okay. So next issue, I want to talk about the design of how you should be thinking about designing your solution to homework 1. I'm sorry, question 1 on homework 8. So again, I used to like racing a lot. I was a good runner. So in this one, I'm having you simulate a bicycle race. So think of each thread as being a different bicyclist. And they are running a 4-segment race. So for each segment, the thread generates a random number between 1 and 8 seconds, which is the amount of time it takes for that thread to complete that segment of the race. So we sleep for that a number of seconds, and then when we awaken, we report to a central timekeeper what our how long it took us to complete that segment. So we basically, as we complete each segment, we tell the timekeeper we completed the segment, and this is how long it took. Okay, so it's like doing, say, 4 laps around a track. Each time you pass the finish line, the timekeeper records your time. Okay, when we're finished, we ask the central timekeeper to add us to a finish queue, indicate we're done. And essentially, the order that you are placed in the finish queue is the order in which you finish the race. So the central timekeeper is keeping track of the cumulative time of each contestant, the number of segments completed, and also whether a new segment has been reported since the last score report. So we'll get to that in a moment. Then, and the finish order of the contestants. Okay, and it is determined by the order in which the contestants are added to the finish queue. So this used to happen that you would be in a dead heat with someone at the finish line, and they'd have a chute that where they basically took your name. So it didn't actually matter right at the finish line who was ahead. It was who got into the chute ahead of the other person. So this is kind of what is going on or being simulated here. So there is, in fact, just the tiniest possibility that one contestant with a lower cumulative time will end up finishing behind a second contestant with just a slightly higher cumulative time. Just so you know, it might happen. Okay, so then also every 2 seconds, your program should print an updated scoreboard showing the position of each of the candidates and whether in the last 2 seconds there have been any new race results reported. So this is going to be a reporter thread. So basically, here is your design. So you have a number of bicycle threads. Okay, so I'll call them B threads for bicycle threads. Yeah. Then you have a centralized timekeeper. And the bicycle threads report scores to the timekeeper, or not scores, report times. Okay, they also, I believe, are going to indicate when they finish, but more on that in a moment. Then we have another thread called the reporter thread. There's only one reporter thread. And it retrieves, or actually, yeah, the timekeeper sends, I'll call them times to reporter, who prints them to standard out. Okay. And then there is a main class that generates all the threads. So generates creates timekeeper, and each of the threads needs to know about the timekeeper. So the timekeeper is a shared resource. It is not itself a thread, it is a shared resource. And as such, it is going to require that you have some synchronized methods to stop conflicts from happening. Okay, but this is your basic design for your program. So if we look back here, so I called the bicyclist will be your contestant, your reporter thread, the timekeeping class. Okay. Another thing that I want you to do just for this assignment, I know that there is already a synchronized random number generator provided by Java. You're not allowed to use it. I want you to also have a shared resource that is the random number generator. So that is going to be another shared resource. So a second shared resource is going to be the random number generator.
We could still use java.util.random, right?
Yes. You just can't use the one in the concurrency package. So you're going to have to create a single instance of it rather than later versions gave you a one that already was synchronized, but I want you to gain some experience with it. So yes, you can use the one in the java.util class. So that's where random comes from. And you will have to synchronize on it. So you're only allowed one random number generator for the entire competition. Okay, you can't have each thread create its own instance of random. Okay, and a couple other things. Your central timekeeper should only use synchronized methods when necessary. So if, again, to avoid unnecessary waiting or deadlock possibilities, you're going to have to reason out whether there can be conflicts or not. Okay, and actually question 2, that you're actually asked to justify whether you made the method synchronized or not. Okay, so that is going to be your basic design. You'll have 2 shared resources, timekeeper and random number generator. And the timekeeper is shared between the different contestants plus the reporter. The random number generator is shared amongst the contestants.
I have a question.
Yes, go ahead.
In my design, the reporter was the shared resource, and it interacted with the timekeeper.
You said reporter was a shared resource.
Right, so my B threads communicated with reporter. They reported through reporter, who would then query a timekeeper.
I don't actually want you to do that. I want actually the bicycle threads to go straight to the timekeeper.
That's okay, I'll just take hits on that one then.
Yeah, because the thing is, you want them to be independent. And the problem with your design is you made them dependent on the reporter thread. So I'd rather
What's the, like, I don't want to stall the class out, but what's the distinction? So the reporter has one timekeeper and there's one reporter.
Right, but it's kind of an unnecessary interaction because you have the thread then going to the reporter thread, which then reports to the timekeeper. So that's a second function call,
Right.
right? So it's a little less efficient.
Okay.
And it's just not as clean. Somehow you don't want let's say I introduce multiple reporter threads, like from the Knoxville News Sentinel, the LA Times, USA Today. Now what are they going to start reporting to different threads? Like maybe contestant one reports. I'm just saying it's now you get some other issues if you have multiple reporter threads. So I guess in answer to your question, it's maybe not a big deal.
No, I understand what you're saying, and I wasn't trying to fight you with it. I was just actually curious about it.
Yeah, so that's kind of it. So
Okay.
okay. Did you two get that too or not? The question? Okay, good. Okay. Let's see. I think there was one other thing here. I want to check something with the reporting to the queue when it's done. Okay. The other thing that you need to worry about for this assignment, this is what I'm trying to, I don't think I actually, nope. Whatever. Okay. Something else you need to consider is there's this finish queue. Where the contestants are being placed in a finish queue. Okay, so they need to notify the timekeeper when they've finished. This is the first time. Remember, all semester, the obvious thing to use here would be something like an array list. Okay, so you don't know, or another thing is an array, but neither of those are meant for multi-threaded applications. So you just have to make sure with the finish queue that whatever you do, that it works. So whatever data structure you choose, it works properly in a threaded environment. So there's two possibilities, and I'm okay with either one. First of all, Java provides some data structures that are meant to be used with in a multi-threaded environment. Array list and array are not two of them. Okay, so they are not meant to work properly in a threaded environment. Java provides some other data structures that are, and you're free to use them. The other thing you can do is you are free to use an array or an array list, but then you're going to have to use synchronized methods with them in order to protect the resource. So it's up to you. Either you use, and I'm not going to tell you what those data structures are, you can look them up, and use one that's already works properly in a threaded environment, or you can use one that doesn't work in a threaded environment, but use synchronized methods to protect it. The choice is yours. Just you need to deal with it. I'm making it explicit that whatever you do, you better make sure that race conditions can't mess up the integrity of that finish queue. So the operations on it, like insert, need to be atomic. Questions about any of this? We good? Okay. That's the case. Let us move on to our final topic of the day, and that is sockets. So the first thing I want to make sure, for those of you at home, are you seeing a screen that says Java sockets on it?
Yes.
Yes.
Good. Perfect. Okay. So we're going to start it today. I don't think we're going to finish today. We'll probably finish on Thursday. So we're going to talk about what are sockets, how clients and servers interact with sockets. We'll then start simple with a single client and a single server. Then we will move up. Then we'll talk about how you need to synchronize sometimes the data objects, just like with threads. Then we'll talk about multi-threaded servers and multi-threaded clients. So this is when you have a server that has to deal with multiple clients. And finally, we'll talk about how you detect when a client or server is shut down, so you can shut down your own end of the socket. So basically, threads are in a shared memory for a process. So with threads, you had two or more threads operating in the same process. Now what we want to do is have two or more independent processes that are cooperating. So before, those threads were like independent processes, but they were all in the same space or in the same process. Now we have independent processes that need to communicate with each other. Okay, so before it was easy, the threads were in the same memory space. Now, the way we're going to communicate is by messages. So before, what we had threads, thread 1, thread 2, thread n, but they're all in the same process. So it's easy for them to communicate. They all are able to access the same variables. Now we are actually have separate processes, and they need to be able to communicate with each other. And the way they're going to do it is with messages. And they're going to go through sockets. Okay, so the way that they communicate is you have a socket and you exchange information over the socket. Okay, so basically a socket is one endpoint of a two-way communication link between two processes. Okay, so typically one end is a server, one end is a client. And the server has to start first. I can't emphasize this enough. If you start the client before the server, the client will fail because it can't connect. Okay, very common, easy to have this problem happen. You have to start the server first. Okay, so the server is listening on a port. Okay, so just probably the same idea as a harbor where ships come in and dock. Okay, pretty sure that's the analogy. So a server is listening on a port. Now, the operating system reserves certain port numbers for itself. And certain applications or services provided by the OS have pre-assigned port numbers. So when you start up your server, you have to go with a fairly high numbered port. And I forget what is the reserved port numbers for each OS. I think it's different for each OS. So at any rate, when you start your server, you choose a port number. If that port number is already occupied, you'll get an exception and you won't be able to start. So when you create, as we'll see, Java has a server socket class. When you try to start it up, you give it the name of a machine and a port. If that port is already occupied on that machine, you won't be allowed to start up. So if you are able to start up on that port, you're listening. And other clients can now issue connection requests. When a connection request is consummated, a socket is created, or a two-way socket is created. So, well, not really. Two sockets, I guess, are created. One on the server side, one on the client side. And they can now communicate over these sockets. Okay, so in Java, the class is called socket server. So in order to boot up the server, you create an instance of socket server. You give it the name of a machine that is running on and a port. Then it calls the accept method. At this point, it blocks, waiting and listening on the port. So the accept method is what causes it to start listening on the port. Okay, so you do any initialization you need, then you call accept and you essentially give up the processor and you wait. On the client side, the client creates tries to create a new socket by making a request to that machine, to the server on its port. And if the server accepts it, then each side gets a socket, okay, that they can use to communicate. So at this point, the client, you can write to a socket and you can read from a socket. So whatever you write to a socket is sent, and the client is sent to the server, and the server can now read from the socket. It can do some processing and then write to the socket, which is then sent to the client. So typically, the client is taking some information from standard in, presumably doing some processing with it, and then writing it to the server. The server is doing some back-end processing, writing the result back to the client. The client presumably then writes that output to standard out. Okay, when both are done, they can close. So that's the basic idea. So always helps to look at an example. And we don't need to look here. We have my own example. So the first thing is going to be an echo client, where the client is simply going to enter stuff and the server is going to echo it back out. So I'm going to show you how to make it work. So I'm on the Hydra machines. Thank you. Huh. There we go. Thank you. Okay. So right now I'm on a Hydra machine. And the first thing I'm going to do is I am going to start up the server. And I'm on Hydra 4. So I give that, and I'm going to choose 10. Actually, I'm going to choose 0 as my port number to show you what happens when you choose a reserved port number. Okay, and I got an error message. Whoops. It's just the port. I didn't need, it knows it's, okay. Didn't need to provide the machine, just the number. That shouldn't have worked. How come it was able to? Okay, so here we have exception caught when trying to listen on port 50 or listening for a connection, permission denied, bind failed. I have no idea why it let me listen on port 0. That seems pretty fundamental. Okay, so that was too low of a number. I'm going to listen on 10,000. So now it's waiting for a client. Okay, so I'm going to go to a different Hydra machine now. So let me log into a different Hydra machine, not that one. Log into Hydra 6. And now I'm going to do the echo client. Now the server is Hydra 4. And the socket or the port is 10,000. What? Couldn't get, is it still running over there?
I think you typed 1,000.
Ah, thank you. You mean on the client side, right?
Yes.
Okay, thanks. Yeah, you're right. There we go. Okay, so nothing's happening right now, but now I type hi Brad, and it echoes back hi Brad. Okay, I send in bye Brad, it echoes back bye Brad. I hit Control D, and it comes out of there. And you can see over here on the server side, it also has now terminated. Okay, so let's see what's going on. Let's break this down. So first, let's look at the echo server code. So first of all, I'm importing stuff from java.net. That's where the socket classes are. And the IO stuff is because I need to wrap the streams in buffered IO stuff. Okay, so the obvious stuff is get the port number from the command line argument, parse it. If it's not a legitimate integer, it'll throw an exception, which I'm not handling. Now, this is a try with resources. So this try statement is okay, this is considered a try with resources. So server socket equals new server socket, and I give it the port number. And I now call accept. When accept returns, it's returning a socket, not a server socket, but a socket, which is a way that I can communicate with the client. Now that socket has input and output streams. And what you normally do is wrap something friendly around them. So here I'm creating a print writer class and wrapping it around the output stream. for that socket, and I'm creating a buffered reader class, and you'll notice this looks a lot like what I did if you think back to file systems. Remember when you opened a file, you first wrapped it in an input stream reader, and then you wrap that in turn in a buffered reader. Same thing. This is just like file IO. So we're getting the input stream and we're wrapping it ultimately first in an input stream reader and then into a buffered reader, making it easy to read it just like us reading from standard in and writing the standard out. So now, basically what I'm doing is I'm reading a line at a time from the client. And while it's not equal to null, so when it's equal to null, it's end of file. So while it's not equal null, I just write the line straight back out to out. Remember, out is my ability to write back to the client. So all I'm doing is printing a line back to the client that I received from the client. And I catch any IO exceptions such as bad port numbers. That's it. So when I get null from the read line from the client, I exit and I'm finished. So that's the server side. Here's the client. So again, my try, I create a new socket. So both the server and the client are creating sockets, giving it the host name and the port number. Same thing, I create a print writer for the output stream and a buffered reader for the input stream. Now notice here's a second input stream. This is from standard in. This is separate. So I get this standard in, and I'm going to read a line at a time from standard in, and I print that line that I get from standard in to the server. Then I read the line that I get back from the server. Now I have to always check to make sure the server hasn't crashed. Okay, because the server might crash. I'll show you that in a moment. So before I go blindly assuming that I'm getting something back from the server, I need to check whether it actually gave me something back. If not, I break out of here and I will exit myself. Otherwise, I will print whatever it is I have, and I will continue by reading my next line of input. Okay, and a bunch of catch statements to about unknown host, not being able to connect on a port. Okay, I shouldn't have to do this. I did not use a try with resources. So that's why I have to do this finally. But if you use a try with resources, you won't have to do all these close statements. Notice I close the end. If I don't use it, I have to be careful about the order in which I close things. So I first close the input and output streams, and I finally close the socket. Okay, so I believe that when I close the the output stream, I think that that sends a signal to the server that there's no more input coming to the server, and so the server can kind of shut down. Okay, so that is what is going on here. So let me show you a couple things. First of all, I'm going to start the server again. And I'll start the client again. So say, hi, Brad. But now I'm going to kill the server. And if we go back here, Right now, it's still executing. Okay, so even though the server's down, it hasn't stopped yet. The reason is it's waiting on standard in. So until remember, any read, any write causes you to relinquish the CPU. So the reason it hasn't exited yet is because it's waiting on me to enter something for standard in. It now gets it, and you see it comes out because now it's able to make progress. So at this point, so it was waiting. Basically what happened was it was stalled right here. Then it got something from standard in, and it tried to write something to this output, which is no longer there. And I'm not exactly sure about the particulars, but somehow they managed to synchronize in here, and it got a null back, it broke out, and it terminated. Now, here's something that every semester gets people. Okay, I am going to restart the server. And I'm going to try to access the server from my laptop. Okay, so I am going to go to hydra4.eecs.utk on 10,000. Couldn't get IO for the connection. Connection refused. And that's because there's a firewall. I checked it with lab staff this morning. So basically, lab staff has set it up so that the higher number ports work on the min-gal subnet, but they don't work for outside computers. So even I don't believe computers on campus, but outside the Hydra/Tesla subnet will be able to get in. So that's why if you decide to play with this example, you need to be on the Hydra machines. Okay, it doesn't work. Now you could also run it locally. So I could certainly run it using localhost. Let's see, I think it's server. Now I'm going blind. I think it's localhost. No, it's just. Okay, now put this in the background. I can say localhost. So I can run it that way on my local machine too. That's another way to do it. Okay, questions about what you just saw? So let me just again show you, go back and show you what just happened. So again, this was the Echo server. It created a new socket server and called accept. It then waited until a client created a socket, and when that happened, the server got a socket and the client got a socket. They share now this communication. So the Echo client was reading lines from standard in. It wrote those lines to the socket. On the server side, it read those lines and it simply immediately echoed them back out to the client socket by writing them. The client read those lines and printed them to standard out. When it finished with reading, it shut down, which caused this socket and this socket to both close. Okay. Now, so we're good with that. That's a fairly simple interaction. Okay. So the next example involves when we need to do some sharing of information. Just like with threads sharing a shared resource, we may also have to have a shared resource with a server and a client. So here we have a data object. So up here it was supposed to say synchronized. Can't easily move this. The top here is saying synchronized data objects. So here we have a data object that we are going to be using to do some of our processing. And the example is a knock-knock server. So basically, we are going to be having the client do knock-knock jokes. So for those of you who have never seen knock-knock jokes, do it on the local. So we'll start up the knock-knock server. Okay, so the server says knock knock. I'm supposed to respond, who's there? And I didn't do it properly. I'm supposed to say who's there with a question mark. So, who's there? Knock knock. Server says turnip. I have to say turnip who? So I repeat whatever the server said, turnip who. And there's always some kind of corny punchline. So turn up the heat, it's cold in here. And then it asks me whether I want another. Say yes. Knock, knock. Who's there? Little old lady. Little old lady who? I didn't know you could yodel. Ah, told you they were corny. No more knock, knock jokes. Okay, so client, the server says bye. Server's done. All good. Okay, so in this case, there is a data object that is keeping track of the joke. And it's keeping a state machine, a finite state machine, with a number of states. So initially, it's interesting. I can see the cursor and you can't. Okay, you're just going to have to kind of follow along then. So there's a waiting state. Is this going to work? Nope. Why can't I make the cursor? Oh, there we go. Okay, so here's the waiting state. So initially we're there and we serve, meaning we print knock knock to the client. So now we transfer to the sent knock knock state and we're waiting a response from the client. So if the client enters anything other than who's there with a question mark, we transition back to this state and send an error message to the client. If the client sends us the proper phrase, which is who's there, then we send a clue to the client and enter the sent clue state. Now the client is supposed to type the clue plus the word who. If the client does not do that, we come back to the sent knock knock state and reissue the clue. Otherwise, if we got the proper match, then we send our answer and the question want another. And we enter the another state. If the client says no, we say bye. We actually do not go back to the waiting state. We're going to exit, but I guess we reset our state to waiting. If the client says yes, we send the knock knock string to the server, to the client, re-enter this state. Okay, so the knock knock object, there's a knock knock object that is operating here. They called it knock knock protocol. So you can see they defined 4 states. No one seems to use enumerated constants. It just seems to be too complicated. So there are 3 states, and you can see they set up their clues. So there's 5 possible jokes. Here's 5 jokes, 5 answers. They have a current joke so that they can iterate through their joke array. They set the state to waiting. So the server is sending the knock knock object the line that the client entered. And based on so we're going to generate an output string. So if our state is waiting, then the output we produce is knock knock, and we update our state to sent knock knock. If we're in the knock knock state, we check to see whether the client typed who's there, ignoring case. If they did, we set our output to whatever the clue is and enter the sent clue state. And if they failed to say who's there, then we produce an error message, and we do not change our state. We return to the sent knock knock state. So you can see this knock knock object, it's simply processing the input that the client gave us and is producing an output string for the server. Okay, and that's basically it. So the server same thing you saw before. It creates a server socket and then waits using accept. When the connection is established, it prints out a message saying accepted the client connection. It does the same thing before that you saw before. It sets up these print and read streams. And then it creates an instance of our knock knock object. And it gets the initial line from the knock knock object, serves that line to the client. And then you can see all it does is it reads lines from the client. It gives that line to the knock knock object, which processes it and returns a line to send to the client. We send the line to the client. And if the line produced by the knock knock object is by, we break out of the loop. Otherwise, we just keep going. Okay, and on the client side, same thing you saw before. We get a socket. We set up our print and buffered readers. In addition, we set up a reader for standard in. So this looks just like the echo. And we have separate strings from the server and from the user. So we start and we read from the server first. And we print whatever the server has given us to output. If the server has sent us by, we get out of here. Otherwise, we read a line from the user. And as long as the user has given us something, we print that line to standard out. We also print that line to the server. And we wait for the server's response. Okay, if the user for some reason has hit end of file, then we print that the client is quitting and we get out of there. Okay, so very similar to the echo example, just with an extra data object added to handle some of the processing on the server side. So Thursday, we're going to talk about multi-threaded clients and servers and how you can implement your talk program, which is homework problem number 3. So we'll be going over multi-threaded clients on Thursday and how to do the third problem for your homework assignment. So with that, I shall let you all go. If you have